All right, so today we have Iñaki Garcia-Etxebarria tell us about the derivation of symmetry structures. Take it away.
Thank you very much, Julius, and thank you very much for the invitation. It's a pleasure, as always. Today I want to discuss some work that I did with Michele. I don't know if he's in the audience. About how to obtain symmetry topological field theories for specifically n equal to 2 theories, but the discussion is a bit more general. So this is based on this work that appeared a couple of months ago with Michele del Soto. Okay, and I should say to start that I'm going to give a Blackboard talk, and one of the reasons for that is I wanted to go slowly, and if there are any questions, please do interrupt. This is not going to be a very technical talk. All right, so this is a talk about symmetries. So I should start by discussing what I have in mind when I say symmetries. And this is closely related in the cases that you have a Lagrangian description to the idea of global forms of the field theory. So these two things go together. So let me review that quickly. And let's consider as an example that's easier to understand. Consider n equal to 4. So per Mills. And I'm going to take it with gauge algebra SU2. By now I'm sure you have all heard that since the original work by Horinsheimer and Tachikawa, and earlier by Gayotto and Moore and Netzke, that this theory comes in different forms. It's not enough to give the gauge algebra, which fixes completely Lagrangian. We need to give a bit of extra information that is often described as the choice of global form for the gauge group. So the idea here is that all the matter in this theory lives in the adjoint. So both SU2 bundles, I'll explain what this is in a second, and SO3 bundles are consistent. So what is this distinction? An SU2 bundle, I define this to be a bundle of SO3 such that spinors of SU2 can be consistently coupled to it. Or if you like, the most natural definition perhaps would be to say that this is a bundle where the transition functions are elements of the group SU2. Right? But I want to treat both of these things in same footing, SO3 bundles and SU2 bundles. So I'm going to view SU2 bundles as a specific subset of SO3 bundles. So I need to define what an SO3 bundle is. I suppose this should happen first. So an SU3 bundle, so an SO3 bundle is defined to be a bundle with SO3 transition functions. Now, in general, whenever you have transition functions in SO3, it's not necessarily the case that you can globally uplift the transition functions to SU2. So there are bundles which you can couple to vectors of SO3, to things that are in the vectorial representation of SO3, but you cannot couple to spinors. From the point of view of SU2, this would be an SU2 bundle where the transition functions don't patch consistently. And just to give you something which is closely analogous, so before I go into that, so these two things are distinguished, the obstruction by an obstruction, and the obstruction to lift in SO3 bundles to SU2 is a characteristic class which I'm going to call W2 of the bundle, so bundle E, which lives in H2 of your manifold, whatever it is, with coefficients in situ. So this is known as the Stiefel-Whitney class. Okay, so this means that W2 bundles with W2 equal to 0 imply that they are actually SU2 bundles. Okay, so mathematically, this is my characterization of what an SU2 bundle is. Precisely, it's an SO3 bundle with vanishing Stiefel-Whitney class. So an SO3 bundle I could understand as an SU2 bundle. Okay, any questions so far? So this seems like.
Could I ask? So just to be clear, say on flat space-time, there are only SU2 bundles then by this.
That's correct. In many spacetimes, you cannot turn on this obstruction because you might not have enough topology to support this class. Yeah. Like S4, for example, and flat spacetime also if you put sort of trivial boundary conditions. Mm-hmm. Yeah, that's true. So much of what I'm going to say will require that you put the theory in a manifold which is sufficiently interesting topologically. In this case, for example, you want the manifold to have 2 cycles. So this thing is not 0, or coming on 0. Yeah, thank you for the question. Any other questions? Okay, so this is a mathematical thing. So there are bundles of SO3 that cannot be interpreted as bundles of SU2 in the standard sense. But we can use this mathematical fact to define what we mean by an SU2 and an SO3 theory. So n equal to 4 super Yang-Mills with gauge group, and I emphasize that this is a group SU2, for example, has partition function. It's a manifold, so SU2, it's a manifold, and for manifold, there's going to be a sum over bundles which have vanishing Stiefel-Whitney class of the standard partition function. So there will be the path integral for connections on this bundle with some adjoints and some Gaussianos of some action, then equal to 4 action, which depends only on the local fields. And I'm from vector space. Okay, so this is one way of defining what we mean by the SU2 quantum field theory. It's something that if you put it in any manifold, when you do the sum over bundles, you only include those bundles that have vanishing Stiefel-Whitney classes. And we can also simulate.
Can I ask another maybe ignorant question? So is it straightforward to put an n equals 4 theory on an arbitrary smooth 4 manifold? Or are there choices involved, or what?
There is. It depends a bit on how clever you want to be, so to speak. Here I'm going to assume that all my 4 manifolds are closed and spin. And then the only choice is the ones I described as far as I know. If a spin with a choice of a spin structure. You can very often do better. You might try to do, I don't know, pin manifolds or things like that, if that's what you have in mind.
Yeah.
And so that's one thing where you could generalize things from what I'm going to say. So yeah, let me write it down. I'm going to assume, just because it will play no role in my talk. I'm going to assume that M4 is closed and spin. Here in this theory, I have a spinors, so I need my manifold to be a spin. My spinors are charged under an R symmetry, so I could get away by doing something a bit weaker, something like a spin C, I think. But let me not get into it. Does that answer your question, Philip?
Yes, thanks.
Yeah. All right. So this is a way of defining what I mean by having a theory with gauge group SG2 in terms of the partition function, and similarly n equal to 4 super Young mills with gauge group SO3 can be similarly defined in the following way as a theory that on a manifold M4 of the same type as above, you sum over all bundles, regardless of whether they have a non-zero or zero Stifler-Whitney class. So you sum over all of them. And then you do the usual path integral. So as you see, the stuff that you have inside the path integral is always the same, totally isomorphic. The thing that changes is the sum over bundles. In SU2, you sum over a specific class of SO3 bundles. In SO3, you sum over all of them. And now for the experts, just to mention it, if you are familiar with the group of with the work of Harun-Sever and Tachikawa, and before that, the paper by Moore and Gayotto and Neitske, they distinguish between SO3 plus and SO3 minus. And the distinction is that in this sum I just wrote, you can include phases in the sum. Right? So the theory I wrote here, strictly speaking, this is SO3 plus in their nomenclature, and I could include some extra phases here that depend on some properties of the bundle. It's basically -1 to the Stifler-Whitney class square divided by 2. Yeah. And that distinguishes between SO3 plus and SO3 minus. But again, this is not something that's going to be very important in my talk, so let me skip it. Okay.
Iñaki,
yes.
In case that you have a product of gauge groups, what do you do?
If you have something like SUN times SUM, for example, then you can have many global forms, and they are distinguished in similar ways. If you have, for example, SUN times SUN groups, like the product of simply connected groups, then the constraint would be that the Stifler-Whitney class, or the analog of the Stifler-Whitney class for both factors is 0. So both bundles that you're summing over have to be SUN bundles. You could have something like PSUN times SUN. There will be first sum unrestricted, second sum restricted to have 0 Stifler-Whitney. And you could have SUN times SUN, everything mod set n. And then there'll be that the first Stifler-Whitney is equal to the second Stifler-Whitney. So there's a natural generalization, but basically you can do whatever you want.
Do you have also 2 types of SP theories?
SP?
Yeah.
Yeah, you have SP and SP mod set. Yeah.
SP and what?
SP mod set 2.
I see. Okay, and they differ by
a similar obstruction. Yeah.
Okay. I see. Yeah.
Good. Thank you. Any other questions? All right. So far I sort of defined the theories by this partition function prescription, but in my talk it will be very important to understand what happens to the lines. So let me just say it because it's probably familiar. In the SU2 theory, we can introduce genuine Wilson lines in the fundamental of SU2. Okay, so what does this mean? In the sum here, I'm always restricting to bundles which are proper SU2 bundles. You can think of a Wilson line in the fundamental as a very heavy particle in the fundamental that's being dragged around. And because the all the bundles that I introduce are pure so proper SU2 bundles. As I drag around this line, I don't have ambiguities with the face. The face is well defined. The whole statement that you call something SU2 bundles, that you can couple spinors consistently to it. So the same thing can be said of Wilson lines. You can put a Wilson line and it's a genuine operator. You don't have to specify the line. Right? So because you impose this constraint on the sum, then you can introduce Wilson lines, which are real line operators. So you don't have to specify a surface attached to that. Dynamical matter is in that joint. And this implies that there's a conserved charge. Conserved set to charge. Measuring Wilson lines. So pictures that we have an extended operator here, and then there's a two surface here. So this is a two surface that measures the centrality, if you like, of the Wilson line. So if you put a Wilson line, a heavy particle which is of a spin 1/2, it might combine with some of the dynamical particles of spin 1 in the bulk and become spin 3/2 or something. But the spin mod 1 will be preserved. And this is what this two surfaces measure. So attached to this, I'm going to define a set to symmetry, which I made not like this. Set to 1 is a one-form symmetry, meaning it measures one-dimensional objects, and it's electric because it measures electric charge.
So the reason the dynamical matter is in the adjoint is important for this is because that's the stuff that can screen. That
exactly. Yeah,
that's what breaks it down to Z2.
Yeah, exactly. Let me. I was going to do that right next. Thank you. So one way of explaining what I said in a bit more detail and what Philip is explaining too is, you mind that you have a screen, you have a dynamical particle here. This is in the joint. And then you have, it's not gauge invariant, right? So there's no relation between these lines. So there's some particle in that joint, and there's some line attached to it. It's not gauge invariant, so we attach a line to it, a Wilson line, and these lines, you can also view them as lines that can end. So they cannot be, whenever you have dynamical matter in that joint, a topological operator measuring their charge. Why? Because you could take a topological operator that's measuring the charge and slide it off until it's the topological operator that's not that's away from the line, and then you contract it to a point and it becomes trivial. So necessarily any topological operator should give you one, it should be a trivial operator when surrounding adjoint lines or anything that's a spin 1. Now we don't have dynamical particles with a spin 1/2 in our theory. So this breaking cannot happen for a Wilson line that's in the fundamental. And so here's one of the most important things in my talk would be that the structure of the spectrum tells you which lines can break, and this tells you which symmetries you have in your theory. And you can do this from knowledge of the BPS spectrum without knowing much more about the dynamics. Is this clear? Yep, great. And similarly, this is not so easy to argue, but it's also true in the SO3 plus theories. We have Tuft lines with, in this case, we don't say that the Tuft line is in the fundamental, but it's a very closely related notion. We can say that the Stifler-Whitney class measured around the line is different from 0. So the idea here is that you get some Tuft line, and you draw a little two surface here in S2, and then you look at the evaluation of the evaluation of the Stiffer-Whitney class of the bundle that you have on this S2, and this gives you say -1. Right, so something non-trivial in situ. So in this way, you have as usual top line is a defect, and you detect the defect by seeing that the bundle is non-trivial or something around the defect. And there's a C2 from magnetic symmetry measuring this. Sorry. So this is mostly stuff that was already in the Generalized Global Symmetries paper. So I'm not saying anything particularly new. Let me try to go to something a bit newer. And that's the idea of symmetry theories. So why is this useful? Symmetry theories are a way of sort of packaging all possible global forms that you can associate to a set of local dynamics. And for example, to us, it was useful to think in this way because in string theory naturally gives you this whole set. String theory lets you choose. So the thing that appears most natural in string theory is not quite the symmetries of the theory, but the symmetry theories of the theory. So let me try to describe this. So the idea is that you start with some quantum field theory in M4, right? So this is some theory, T on M4, and T could be SU2 or maybe SO3 or whatever you want to put here. It could be non-Lagrangian, it doesn't really matter. The picture works in here. And the idea of the symmetry theory is that very often what you can do is you can sort of open up the theory and split it into this sort of sandwich in which you have some 5D theory here, which is in our case topological, so I'm going to call it the SIM-TFT, the symmetry topological field theory, living here. And this symmetry topological field theory has a gap boundary that you get to choose. And it has a set of local degrees of freedom. I'm going to call this small SU2, as in algebra SU2, relative. So it's relative. And the word relative comes from work of Fried and Telemann from the year 2012. Okay. Fried and Telemann, what they did in this paper is a way of understanding theories in which, in the modern language, you don't quite choose the global form of the symmetry yet. So a way of talking about the theory before choosing the global form. And the idea is that you attach it to a 5D theory, like here. And if you want to choose the global form, you pick a second, this time gapped boundary. This one's gapless, this one's gapped. You pick the gap boundary, and the boundary conditions are in correspondence with the global forms. So there's a gap boundary, I'll describe this more. There's a gap boundary for SU2, a gap boundary for SU3, and so on. So all the possible choices you could have done for the symmetries in your equal to 4 theory, you can view as different choices of gap boundaries here. And if you now take this sandwich and collide the gap boundary with the ungap boundary, you get back your standard 4-dimensional theory. But in doing this, we have separated what is local, the local degrees of freedom, from what is global, which is a global structure. And as I mentioned before, in string theory, what you naturally obtain is this thing here. Okay, any questions?
Yeah, so it seems this setup seems to have lots of topological possibilities. The topology of the 5D theory, does the gap boundary have to have the same topology as the relative boundary and things like that? I mean, I think, or do you always have in mind that it's the gap boundary and the relative boundary have the same topology and this thing is just an interval cross?
Oh, yes. Yeah, good question. Eventually, I want to collide these two. So this is much more general, of course. The idea of relative quantum field theory is that I have a boundary and I extend it in one dimension higher, and this can have all kinds of topology I want. That's completely true, yeah. But my goal here is to construct a four-dimensional theory in M4. So I'm going to always be thinking out M4 times an interval. But you're totally right. I could do many other things. It doesn't change much because the wait, it does change some things. Yeah. No, for my purposes, I really want the interval because I want to eventually have a theory defined on M4. If I were to choose different topologies here, right? So this would be an M4, and this is something that's some other N4, which is connected by some bordism. There's nothing mathematically wrong with that, but maybe I wouldn't call that a proper four-dimensional theory. And there's nothing wrong with it, just a 5D theory.
Mm-hmm. Okay, thanks.
Mm-hmm. Yeah. Right. So let me say a little bit more about what this SymTFT is and what it does, and then I will explain how to derive it. I should say one thing. This is just a little side remark. This is not the complete picture. So with anomalies, so that is, if you care about anomalies, you have a slightly different picture, not very different. So if you have your M4 and it has an anomaly, these days we like to think of anomalies as, can you see this? Yeah. Maybe just go. We like to think of anomalies as some invertible theory in 5 dimensions also. So there's an anomaly theory here. Again, this is more for the experts. It's not going to be playing a role here, just to complete the picture. So I can do the same picture essentially. So I open up the sandwich. I get the relative theory here. I get my SymTFT. And I get the anomaly theory here. And the big difference between what I just said and what I'm saying now is that now this is a gapped interface. So the SymTFT will change. It will include anomaly in this case. So the SymTFT I will write will include anomaly. And then there will be an interface between that SymTFT and some invertible anomaly theory. Yeah. For today, I just want to understand the choices of global structure. So I'm going to forget about the anomaly, and my picture is this kind of interval picture. But this just to emphasize that the whole thing plays perfectly well with the idea of anomalies. Okay. So today, is not the most general option, but today, SymTFTs are set n gauge theories. In 5D. Okay. This is the basic case that gives rise to all this structure reading between the lines. It's enough to understand what happens with discrete or finite gauge theories in 5D, in particular set n gauge theory. So we can describe, so example, set 2, but everything I'm going to say generally is very easily more generally, just to make it a bit concrete. This is a theory with action as follows. 2 by I times 2. So the 2 of set 2 is this 2 here. If I have the set k, this will be k. Integral on your 5-dimensional manifold. of some field B2 wedge DC2. And a word on conventions. The integral of B2 and the integral of C2, they are integral. There are kind of two conventions in the literature, or three really. But here I'm going to choose the one in which B2 and C2 are integrally quantized.
Do you also need products like Z2 squared topological field theories? I mean,
that's true. That's true. Yeah, indeed. That's true. So for some cases, I will want like SO for K. I will want SO Z2 times Z2. Yeah. In fact, the case I will present is slightly more general, and it will include that case as a subcase. Okay. But it's not a big generalization from here. And sorry, what I said here was slightly sloppy. I don't quite mean that the periods are integral. Are integral periodic, have integral. Yeah. Define mode 1. So that's what I mean. They have periodicity 1, the periods. Okay. So other conventions that sometimes they have periodicity 1/2, and sometimes they have periodicity 2 pi, or some other combination. But mine is this one. That is true. Right. So with that convention, the K is here in front, multiply. Okay, so this theory is gapped. It has no propagating degrees of freedom, and that's easy to see. The equations of motion are as follows. D of B2 is 0, and D of C2 is 0. Right? The variation with respect to B2, I mean D of C2 is 0. I integrate by parts and vary in C2, I get this other equation. So this sets these fields to be trivial locally, but there's still interesting stuff in this theory. This theory has non-trivial extended operators. And they are simply the holonomies of this field. So I'm going to call the operator B that depends on two surface sigma. It's going to be the exponential of 2 pi I integral over sigma of the holonomy. And similarly for some other operator, C, which is a holonomy. Okay. So if I can argue that these operators are non-trivial, the theory is non-trivial in the phase capped. So let me argue that it's non-trivial. I'm going to compute the correlator and show the correlator is not 1. So introducing the sigma in the action, equations of motion become -2 dc2 in my convention plus delta of sigma equal to 0. Right, so the idea here, let me go back to the action. If I, in some correlator, I put this B of sigma is the exponential of this term, I can write this term as B2 cap product with delta. Then I have B2 cap product with DC2 minus the delta with a factor of 2. And then I derive with respect to C2 and I get this equation. Okay, is that clear? Okay, so the equations of motion have been modified. And then this implies that in the presence of B sigma, we have expectation value for this operator, the exponential, so sigma, exponential of 2 pi I integral over sigma prime of C, pi stocks, answer. So choose a B3 such that the boundary of B3 is sigma prime, exponential of 2 pi I B3 of the C2, equation of motion, the one here. This is the exponential of 2 pi I over 2 integral over B3 of the delta function of sigma. And this is by definition the exponential of 2 pi I over 2 of the linking number between sigma and sigma prime. Right. Recall the definition of the linking number is you have, in this case, two surfaces in 5 dimensions. You fill one of them, and is the intersection of the filling with the other surface. So this is what I computed here. So this is the linking between the two surfaces in 5 dimensions. And you divide that by 2, and this gives you something depending on the linking. So equivalently, you get that the correlator of these two things is this phase that I just computed. So if you like -1 to a linking number sigma sigma prime. Okay. So this theory is non-trivial. I have two operators that if they link, I get a -1 set. Even if it's gapped, there's some non-trivial operators in the theory. Is the logic clear here? It's a fairly straightforward derivation, but it was a little bit quick. Okay. So this implies we can understand this. As let's say C sigma prime being charged under B of sigma. So what's the idea here? The pictures, I have two cycles that are linking, sigma and sigma prime, not properly B of sigma and C of sigma prime. And I can deform this configuration until these things don't link anymore. So this will be a B of sigma tilde and a C of sigma tilde prime. So these are the deformed ones. But in doing the deformation, because they cross, they will pick up a phase, which is the charge really. So in this case, so phase. And now these are operators, which are topological operators, which don't link with anything, so I can contract them to a point. So I get simply the phase, right? But when you cross a topological, when you cross a topological operator along another operator and you get a phase, that means that the operator you're crossing is charged under the symmetry defined by the topological operator. So in this way, we have learned that B is charged under C, or currently C is charged under B. They're both topological, so you can interpret this phase in either way. Okay. So these are two topological operators which both define symmetries, and the symmetry generator is charged under the other symmetry. So that's fine. Okay. So it's a fairly interesting theory in this way. And in terms of the Hilbert space, on some spatial slice, right? So put sigma and sigma prime inside M4, take a spatial slice and put your operators in the spatial slice. what do these operators do? Well, now that I know that one is charged under the other, I know how the commutator between two operators in which one is charged under the other is, right? So this implies that the commutator of B sigma C sigma prime cannot be 0 because one is charged under the other. I'm working through the details. It's not hard to find that this is -1 to the intersection in this case, sigma to sigma. Okay. This is the Hilbert space statement saying that C has a charge under B, or if you like, B has a charge under C. And sorry, maybe this was not incorrect, but I'm using multiplicative notation, so just to make things clear. Let me expand that. So this is -1 sigma sigma prime. Okay. Please. Right. So this is the statement that B is charged under C or C is charged under B with this charge. And this is something that was known from before. In fact, if you just look at the BF theory, there's a very nice derivation of this same expression without going through all the discussion I just went through in a paper by Witten from 98.
I'm sorry, a little confused. You're putting the four-dimensional slice. So what do you mean by the linking number? Do you mean the intersection number now?
No, yeah, sorry. I went a little bit quick there. In 5 dimensions, the linking number, the standard linking number. But in 4 dimensions, in this commutation relation, is the intersection pairing.
Okay.
Right. Yeah. So just to give you the intuition for why this is true. Well, 2 ways of understanding this. The linking pairing and the intersection pairing are related by squishing things together, right? If you have 2 things that link and you push them to the same plane, they will intersect. But this may be a little bit sloppy. If you want to see the details, you can go to Witten's paper, and the argument is that you go back to the original action, this B wedge F action, B2 wedge DC2. In this action, B2 and C2 are canonically conjugate variables. So they don't commute. They're canonically conjugate fields. So they don't commute with a commutator that depends on the position. And now you have 2 integrals of B2 and C2 exponentiated. So you will get a contribution to this sort of finite commutator I drew here, coming precisely from the points in which B2 and C2 appear at the same point. Precisely at those points, you get commutations, which are non-trivial because of the classical commutation relation between canonically conjugate variables, and that's why you get the intersection number here. The rest of the operator commutes if they don't touch. All right. All right, so this was a long discussion, but hopefully it was useful because I ended up in a place where it's easy to handle. I have a couple of operators that don't commute up to a phase. This is the standard problem in quantum mechanics. You have operators that don't commute, and you want to understand how they act in some Hilbert space. But here everything is very easy. These operators are C2 valued. So it's really a discrete Hilbert space with just a few vectors. So a discrete set of operators. So it's a bit easier than the standard problem in quantum mechanics in which you have a continuum of x's and p's. Here you just have, even if these ones don't commute in the same way that the x's and the p's don't commute in the Heisenberg algebra, you have much fewer operators to worry about. So the problem is much easier to handle. So now we went through all these exercises because gap boundaries are classified by studying, or you can classify boundaries by studying the Hilbert space on which B and C act. Right. And that is the following. If you want to specify a boundary condition for, remember the picture we had, something like this. So we are looking at this capped side. Then you want to give a state in the Hilbert space. And that means that you have to specify the expectation value of P or the expectation value of C, but you cannot specify both at the same time because they don't commute. So boundary conditions, in this case, are easy. Boundary conditions. So basically you can choose, there's three types of boundary conditions. You can choose Dirichlet for P. You can choose Dirichlet for C, and you can choose Dirichlet for B plus C, or B times C, multiplicative notation. Right. You have these operators that don't commute, and to specify a state or a boundary condition, you want to specify a maximal commuting set of operators. So in this case, it will be the B or the C or the product of both. Those are maximally commuting sets. And then you give a BEF to those as you go to the boundary. Right. So these are the boundary conditions that you have. Dirichlet for B, C, or BC. And you can then associate this to, for example, SU2, SO3 plus and SO3 minus. Okay, so at this point, it seems like a stretch. I have three things, three theories, and I'm just labeling them. But there's of course, much more that justifies these choices. So first of all, remember that just in quantum mechanics, if you have a eigenstate of a momentum, it's a sum over eigenstates of position with phases. It's like a Fourier transform, right? The eigenstate momentum is e to the IPX. The eigenstate momentum is e to the IPX. What this means is that in this finite setting is that Dirichlet for C is the same thing as Neumann for B. So if you're fixing C, that means that you're summing over B. And this should remind you of the SO3 theory being a sum over all Stiefel-Whitney classes. In fact, you can go a little bit further and argue that the Dirichlet boundary condition for B, it doesn't have to be that B is trivial at the boundary, it could be B is some phase at the boundary. So you choose it as you like. And the precise Dirichlet boundary condition that you choose is precisely the choice of background for the one-form symmetry that you have. You can also look at the operators. So which operators do you have? You have B and C in the bulk. Whenever you choose Dirichlet for B, so let me assume just for drawing the picture, that you choose a Dirichlet boundary condition for B, then it is consistent to stretch a B operator in this way, from one boundary to the other. And when you collapse, what will you see? Well, this is a two surface, and it has a one surface here on the, so a line on the boundaries. So this thing here is going to become precisely the Wilson line in this picture, once I contract. So the B operator with the Dirichlet boundary condition can end, and its endpoint is the Wilson line, it should be identified with Wilson line. The C operator cannot end with this choice of boundary conditions, but it stays on the bulk as a two surface, and when you contract, it's a topological two surface in your theory. So it's going to be a symmetry generator. So B becomes the Wilson line, and C becomes the symmetry generator. And the fact that I went to some pains to prove that B is charged under C, or C is charged under B, now becomes the fact that I wanted to state, that the Wilson lines are charged under the symmetry generators. More, well, in specific configurations like this one, You can study the action of SL2C on the boundary. You will see that B and C are exchanged in the same way that S duality exchanges SU2 and SO3 and so on. Okay, so you can convince yourself that all the things that you know about the global structures of SU4 can be reproduced by this picture. And in this very nice and simple way, you have a discrete gauge theory here with these two operators. I more or less described everything there is in the gauge theory in just in the last 20 minutes. And then you just compute the boundary conditions, which is a simple problem of classifying the states on a very finite quantum theory. So something very straightforward.
Iñaki, question?
Yeah.
Can I?
In the correspondence with the states in the quantum mechanics,
Mhm.
And this is a question for Zn, where n is larger than 2.
Mhm.
Is it always that they're in correspondence with gapped boundaries, or may they be in correspondence with gapped interfaces with invertible theories?
No, you are right. Yeah. Yes. I think some of these cases will leave. Thank you for the clarification. In some cases, some of the gap boundaries lead to one-form symmetries, and in principle, these remaining one-form symmetries may have anomalies.
Yeah.
And in that case, this should be understood as a clarification of interfaces. Yes.
Okay.
I think it was you who taught me the context. Yes.
Yeah, can I ask also maybe an easy question? So in the BC case, what would play the role of the symmetry? Because then BC, you mean really the product of the two.
The product of the two operators.
Then what would play the role of the symmetry if we impose Dirichlet conditions?
That's a good one. Let me think. I think it's. You have to think for a minute. I think it's going. The thing that happens is that BC itself becomes trivial if it's in the once you squeeze, or if you like, once you take the bulk operator and you move it to the boundary, it becomes trivial.
Mm-hmm.
So in this case, we'll get that BC itself is trivial. It's a trivial operator. So B and C end up identified. So I'm tempted to see that you could choose B or C because in the final theory they're going to be the same operator.
Mm-hmm. I see.
Yeah,
and actually, I was wondering, because of the equality you wrote above the commutator, then if you take sigma equal to sigma prime, I guess it doesn't.
Yeah.
You should not consider when they have a common component, I guess, this equality.
No, that's okay. Here, remember, I'm restricting myself to spin manifolds. For a spin manifold, the self-intersection is always even. Yeah, so there's no.
I see. Thank you.
Yeah, thank you for the questions. All right. So I have a few minutes left. Let me sort of state what the goal of our paper was, and just give you the answer, because at this stage it's not very difficult. Right. So our goal, we want to obtain the SIM-TFT, more precisely this discrete gauge theory part I've been talking about, on the Coulomb branch, from data on the Coulomb branch. And here the intuition is that this is a gap theory. So it should be robust. Under given BEVs, deformations. Uncharged under the symmetry. Right? So here we are talking about one-form symmetries. For going to the Coulomb branch, you turn on Coulomb branch operators. These are point-like operators. They're uncharged under one-form symmetries. So if you turn on these operators, the symmetry structure should not change. Okay, so that was our sort of intuitive motivation, but we wanted to check if this actually works. And indeed, it seems to work. So what we found, for details, I'm happy to discuss details after the talk, but just to finish on time, I'll refer you to the paper. Let me give you the final answer that we found. Just by looking at the Coulomb branch, and there's lots of fun things you can say about Maxwell theories that I didn't have time to say, is that the SymTFT action as obtained from the Coulomb branch is basically the following. Is the integral over a 5-dimensional manifold of some intersection matrix here. So this is the, I'll explain this in a second. So some pairing matrix, antisymmetric, of some B alpha cap D B beta. All right. So with this is starting to look a little bit familiar. So here alpha runs from 1 to 2R, and here R is the rank of the field theory. So this is the final answer for n equal to 2 and 4, n equal to 2 and 4. So this is the dimension of the complex dimension of Coulomb branch times 2. And you have a bunch of fields, B, parameterized by this. These fields are of period 1. And then you have a matrix here, which is the BPS Quiver intersection. Sorry, I'm using the right words here. The BPS, intersection pairing for the BPS Quiver. Okay, so this is fairly straightforward. Even if you don't know a Lagrangian for your n equal to 2 4-dimensional theory, very often you know the BPS quiver. So all you need to do is take the intersection matrix that defines the quiver, and this defines for you a small generalization of the B wedge DC theory I was talking about before. And this is the TFT. Now, this might look much more complicated, but it's not much more difficult because of the following fact. Every antisymmetric pairing Q alpha beta can be block diagonalized over the integers. So even if your quiver looks fairly complicated with lots of arrows, but you can always block diagonalize it and write it in a form that's very easy to analyze. It's 0 minus n1, n1, 0, 0 minus n2, n2, 0, and so on. So you can always put your intersection pairing in this form, by integral change of basis, which doesn't affect the integrality properties of the theory. And then it reduces to R copies of the problem I just discussed. Okay, so all you need to know really is how to deal with set K discrete gauge theory. As Philip was pointing out before, it's not always the case that you have just one block which is non-zero, so you could have two which are non-zero, and it's perfectly fine. But this problem is decoupled, so you can, when it comes to classifying boundary conditions, you just have two separate problems.
So Iñaki, physically, this the matrix Q, it's describing like the electromagnetic charges of BPS particles, and is that?
Is the Dirac pairing between the particles. Yeah. So
okay.
Yeah, exactly. So just to define Q, and with this I will finish. The dynamical states live on a lattice. We call it gamma with generators gamma I. And then Q is basically the Dirac pairing between Q alpha beta, is the Dirac pairing between the corresponding generators. Yeah. Okay, thank you very much. With this, I will finish.
All right, great. Let's thank Iñaki. Do we have questions?
One comment, I skipped a lot of things, so if anybody feels like they want me to go deeper into anything, I'm happy to do so.
So you said that there are some fun things you can say about Maxwell. Did I hear you correctly?
Yes, yes.
Can you tell us something fun about Maxwell? I would be interested. So everyone reflects.
I think the slogan, I don't know if it's the slogan, but the thing I got out of this paper is that pure Maxwell with no matter is probably the most subtle theory of all, the free U1 theory when it comes to this story. So let me go back to the picture I drew originally. Our whole purpose in this paper was to do this sort of picture for U1 theories with massive stuff. And in particular, U1 theory should be relative in some sense if this picture is to work. Now that's something that's a little bit uncommon. You don't think of the U1 theory having different global forms. But once you introduce charged matter, it's not hard to argue that indeed you get lines that are not mutually local, for example, as including between the lines. Here's the idea. If you have that your electric states have charge 2, and those are the dynamical states, you can introduce at-off lines that are half integrally quantized. The flux along the at-off line is 1/2 the minimal unit of flux. And that's okay because all your electric particles have charge 2, so the holonomy they get is times 2 and everything's consistent. So you can put half integrally quantized at-off lines. Generally, we don't do this in the U1 theory because you can always rescale the charges. Right? You say, okay, if all my electric charges have, if all my dynamical particles have electric charge even, then I'll just scale the charge by 1, by 2, so I divide by 2 the charges. This multiplies the flux on the top line by 2, and then everything is a standard picture. But once you have dions, this is not true anymore. You can just rescale the problem away. So, for example, in the SU2 theory, let me give you the charges. In SU2, just n equal to 2 SU2. Oops. So what do you get? Let me do the values. Right. So here you have dynamical particles with charges in some conventions, 0, 1, and 2, -1. All right, that's fine. So the possible Wilson lines, Wilson, I guess, Toft lines, have charges. They are generated by the following lines. One is 1, 0, the standard Wilson line in these conventions. But then there's a couple of funny ones. You have 0, 1/2. And 1, 1/2. And now you see that these lines are not mutually local. Right? If you try to compute the Dirac pairing between these two, you get 1/2. That means that there's a holonomy as you take these lines around each other. So in this Maxwell with dynamical particles, you can introduce fractionally quantized, in this case in the magnetic sector, lines. And because this fractional quantization is allowed, and that's basically because the spectrum is not complete here, you get lines which are not mutually local. And you reproduce the structure from the non-abelian case. So this is something that's, well, once you see it, it's not very surprising. But the funny thing is that if you didn't have the dynamical particles at all, you wouldn't have a reference frame. So you can put any arbitrary real numbers you want here. And then you have a huge spectrum of non-commuting lines, right? And you have an infinity of possible global forms for pure Maxwell with no matter. And that's because that's the mother of all theories, if you like. All possible global forms that you could ever construct have to be in the free theory. And putting matter kills many of these possibilities. So yeah, the free theory is the most complicated one, which was something I found really amusing.
Very nice.
Mm-hmm. And that's because the universal one, everything comes from it.
So do we have more questions?
Can you learn anything new about different global forms and Tufte anomalies, discrete Tufte anomalies of non-Lagrangian theories?
Yeah, well, yes, in the sense that there were some cases where the BPS quiver was known and the string engineering was not known. And because the input to these calculations is the BPS quiver, or the intersection pairing in the BPS quiver, we could obtain some results about those theories. So in that sense, it's new. If sometimes you know more about the free theory than the string construction, in those cases you can apply this prescription. It's mostly about some examples that were not understood from string theory before. So we have some in the paper. Many of these that I'm going to say have string engineering, but just to mention them, things that were known before, were not completely known before, were the, for example, the Minahan-Mechensky theories at rank 1. So with this prescription, you can see they don't have a one-form symmetry, the E6, E7, E8, and the H0, H1, H2. So you can check it. And we had also some of the theories in the classification by Philip, Mario, and collaborators that we looked at. We couldn't do all the rank 1 theories, for example. We will have like to, but some cases don't have known BPS quivers. For example, the n equal to 3 theories don't have known BPS quivers. But this gives you maybe a line of attack to those, complementary to string theory.
More questions? So if we have no,
I have one question, which is you have a Dirac pairing that you derive, or you're identifying with the intersection matrix for the BPS quivers, but I don't know of an example, but isn't it a logical possibility that your charge lattice is not actually spanned by the or generated by the BPS lattice?
It's definitely a possibility. Yes, in fact, in string theory, in type 1, there are states like type 1. We generally say has gauge group ISO 32. That's not true. It's spin 32 mod C2, and the spinner is a non-BPS state. Mm-hmm. So if you were just looking at the BPS states of type 1, you wouldn't see this. So indeed, there are counterexamples, and I don't want to make strong claims. I don't know any counterexample in the context of n equal to 2 four-dimensional theories. Yeah. But yeah, I agree. It's possible loophole here.
All right, more questions? If not, then let's thank Iñaki again.
Thank you very much.
Stop the recording.